All right, we're right back at it with water again. This is the third chunk of this first lecture series. We're going to talk right now about pH and acids and bases. We'll take some of what we learned about polarity and water being the universal solvent and build on it, but certainly we're going to be talking about acids, bases, pHs, and buffers. And we'll have one more chunk, a fourth chunk for this lecture that follows, where we'll deal with pKa as well. Again, as I mentioned at the beginning of the first lecture, I'm well aware that this is review for many of you, but these are concepts we're going to be returning to again and again in biochemistry, and so I want to make sure that everybody has a solid footing on these more chemically processes and ideas. So let's talk about acids and bases first in general before we tie water into it. An acid, in its most simple definition, is a hydrogen ion donor. That's what an acid is. It's anything that can give up a hydrogen ion to solution. A base, then, is the opposite. A base, simply put, is a hydrogen ion acceptor. Hydrogen ions are also referred to as protons, and I may flip between the two interchangeably. Just keep in mind that we always mean a hydrogen ion, a single hydrogen atom with a full positive charge. Strong acids and bases are things that do their dissociation, things that lose or gain their hydrogens very rapidly. So if we have a strong acid, all we really mean by calling it strong is that when you put that acid into some solution, it's going to very, very readily and rapidly give up its protons. We know it's giving up protons because it's a strong acid. A strong base is going to very quickly and readily absorb protons from a solution. That's why it's a strong base. So this idea of dissociation, of giving up your protons or having protons stolen from you, is dissociation. So this is probably the simplest generic reaction we could possibly devise for an acid. Here we have some molecule. We'll call that molecule A. That's an acid molecule. And it is linked to a proton. It has a proton. So this is an acid. When that acid is put into water or some other solution, we see that it has lost its proton. That's why it's an acid. This proton has been donated to the solution, and the acid is now dissociated. Some of you might remember that we now would refer to this as a conjugate base. This conjugate base is ready to receive a proton, and if it receives a proton, acting as a base, it'll go back to where it started. So the dissociation of protons from acids can be measured, how quickly that molecule gives up its protons, and when it's measured we can give that acid a dissociation constant, which is a measure of acid strength. For the dissociation constant, the higher the number, the more that molecule dissociated from its proton, the stronger of an acid it is. And we can calculate the dissociation constant. We won't in this class, but you could calculate the dissociation constant by waiting until this acid reaches an equilibrium, and then measuring the proton concentration, multiply it by the conjugate base concentration, and divide all that by the concentration of intact acid that remains. Whatever that value is gives you your dissociation constant. And as always, when we're talking chemistry, these brackets refer to concentrations, and those are concentrations in molarity units. Those are molar concentrations. Each acid has its own particular Ka, its own dissociation constant. It never changes for that acid. It's a permanent property or characteristic. I like to think of it as the acid's eye color. Eye color can't naturally change, and neither can Kas. Again, as I told you, the larger the Ka value, the more dissociation we see upon solution, the more protons that are released, and therefore the stronger the acid. And we've already defined this as the conjugate base over here, and this is the acid before it dissolves. So it sounds like we just gave up protons to solution, and we would expect there to be free protons in solution, but the truth is that's not really true. Water itself can act as an acid or a base, and in the case of we just described, where an acid is dissolved in solution of water, water acts as a base. It absorbs that proton, and in doing so it becomes H3O+. That is also referred to as a hydronium ion. And so that proton is free, quote unquote, in water for a very short time. Instead, that water kind of gloms on, instead that proton released by the acid kind of gloms on with a water molecule, making it H3O. Water itself can also dissociate, being an acid, and make itself a base. It can neutralize itself, and we can see that water can dissociate into a hydroxide ion, which is now a conjugate base, and can assume or absorb a free proton and the proton that it gave up. So anytime water gives up one of its two protons, it's acting as an acid, and it leaves behind the conjugate base hydroxide ion. Water does do this normally, and water will reach a concentration gradient between dissociation and association. Water dissociates to equal concentrations of proton and hydroxide ion, not surprisingly, because anytime you get one, you have to get the other. These add up to give you water. And if you allow water to freely dissociate until it reaches an equilibrium, and then you measure the amount of free proton from water or free hydroxide ion from water, you'll find that you have about 10 to the minus 7th molar of each. So when water dissociates, the concentration of free proton from water is about 10 to the 7th molar. And the concentration of free hydroxide ion per water molecule is about 10 to the minus 7th molar as well. Other acids dissociate to proton concentrations as high as 10 to the minus 1 or as low as 10 to the minus 14. And we can get everything in between. Strong acids would, of course, be more towards the 10 to the minus 1. They give up lots and lots of protons. And very, very weak acids, obviously, are going to be more in the range of 10 to the minus 14. They really don't want to give up their protons at all. This gets pretty cumbersome if you look at it, all these exponents and everything going on there, also the negative signs. And so scientists a long time ago decided to make this easier to look at, easier to write and talk about, and so they just took the log of these values. So if you take the negative log 10 of these dissociations, these measurable dissociations, you get your pH. And so if we go here, back to our water example, we said that when water dissociates, we get a free proton concentration of about 10 to the minus 7th. We can take the negative log base 10 of 10 to the minus 7th, and if you plug that into a calculator, you'll see that that value is 7. In other words, the negative log base 10 of the value 10 to the minus 7th is positive 7. Well, that means that the pH of water is positive 7, and that's no surprise at all. Water is neutral. We knew that. Acids have lower pHs than 7 because acids dissociate more than water does. They give their protons up in higher concentrations. Bases have pHs that are higher than 7 because bases hold on to their protons much more. They like having protons. They'll accept protons. And so bases don't readily dissociate into protons, and so they have pHs that are higher than 7. Hydrogen chloride is known to be a very strong acid. If you allow hydrogen chloride to reach an equilibrium in water, you can measure a free proton concentration due to hydrochloric acid as 10 to the minus 3rd molar. If we take the negative log base 10 of that 10 to the minus 3rd, we get a pH of 3, a very acidic pH. Not surprising, because HCl is acidic. If we consider sodium hydroxide instead a strong base, we can start off with a dissociation concentration of sodium hydroxide that's 10 to the minus 4th molar. Again, this is a strong base. It completely dissociates in high numbers. If we look at that and we apply the same math as we applied to water and hydrochloric acid, we would get a pH of sodium hydroxide as being 4. But we have to ask ourselves, does that make any sense? That a strong base would have an acidic pH? No, that doesn't make sense. So, if we take the negative log base 10 of 10 to the minus 4th, we will get the hydroxide ion concentration, because there are no free protons here. That 10 to the minus 4 represents this hydroxide ion here. In order to do pH, we need the proton concentration. So let's go back to water. In water, the free protons and the free hydroxides always come out to 10 to the minus 14th. Always. If we're talking about sodium hydroxide giving us a hydroxide ion concentration of 10 to the minus 4, and we have to always get to the 10 to the minus 14th, that means our proton concentration is going to be 10 to the minus 10th. 10 to the minus 10th free protons, along with our 10 to the minus 4th hydroxide ions, is going to get us to the 10 to the minus 14th we're after. So it's 10 to the minus 10th we want. The negative log of 10 to the minus 10th is 10, and that's a pH that makes sense. pH of 10 for a strong base is well above 7. That's where we expect it to be. So always apply this common sense rule, this common sense method. Acids will have pHs lower than 7. Bases will have pHs higher than 7. If you're manipulating the numbers and you don't get that trend, play with those numbers some more, because something is probably going wrong in either your math or in your thinking. So we can make dissociation constants as easy as we make proton concentrations. We don't have to have these large, cumbersome numbers of 10 to some wacky exponent. Instead, we can take the negative log base 10 of our Ka values. And just as we got our pH concentrations, we can get our P dissociation constant calculations or values. So if we take the negative log base 10 of our dissociation constant Kas, we get pKas. The smaller the pKa value of a molecule, the stronger of an acid it is. Small pKa's mean strong acids. The higher the pKa value, the weaker that acid, or the stronger the base. So here's how I like to think of pKa. pKa is defined as the pH of a solution where 50% of the acid is dissociated. Now that's a key concept to keep in mind, and I'll say it again. If you have an acid in solution and it is exactly 50% dissociated, that means 50% of the losable protons have been lost, and the other 50% of the losable protons are still retained by the acid, you are at your pKa. Whatever the pH of that solution is at that moment is the pKa of that acid. In other words, if the pKa of a molecule is 11, then you must get the pH of the solution that molecule is in to a pH of 11 in order for that molecule to lose 50% of its protons. And still, even then, at pH 11, the other 50% of the molecule's protons will still be intact. That means you got to get very basic in order to lose those protons. That means you need a lot of hydroxide ions around in order to get that molecule to lose 50% of its protons. Does that sound like a strong acid to you? Does it sound like a strong acid? Remember, strong acids are molecules that readily give up their protons. Does it sound like a strong acid where you have to have tons and tons of hydroxide ions around all the way to a pH of 11 just to get that molecule to lose half of its protons? No, that's not a strong acid. Strong acids have low pKa's because they'll give up their protons even in acidic environments. In biochemical systems, including the human body is a biochemical system, you better believe it. Most acids we encounter are weak acids with high pKa's. So this brings us to the Henderson-Hasselbalch equation. Not because I want to do it, but because we have to do it. Keep in mind, we're all as miserable as the rest of us when we have to apply this kind of math to biochemistry. I will point out, before we go on, for those of you who are pre-med, especially pre-vet, for those of you taking the MCAT exam or MCAT-like exams, you're going to have to know the Henderson-Hasselbalch equation inside and out. There will be questions on this material in your MCAT or MCAT-like exam. The Henderson-Hasselbalch equation is useful to us because it connects the pH of a solution at any given time with the pKa of that molecule. pKa, remember, is a characteristic, it's a property, it never changes. A molecule's pKa is always that pKa, it will never change. And with this correlation between pH and pKa, the Henderson-Hasselbalch equation also allows us to predict the concentration of intact acid and dissociated conjugate base. Back to our original example, remember when we say intact acid, we mean a molecule that has retained its protons, and a conjugate base is a molecule that has lost its proton, thereby being an acid, leaving free proton in the environment. This is the Henderson-Hasselbalch equation. It's simple and straightforward. It states the pH of any solution at any one time will always be equal to that molecule's pKa plus the log value of the proportion of conjugate base divided by intact acid. In other words, whatever conjugate base is present in that solution divided by the acid that's still there, take the log of that proportion, add it to that molecule's pKa, and that's the pH of the solution you're in at that moment. Actually, before I go forward, getting back to our idea of saying that the pKa is defined as the pH when half of the molecule has dissociated, we see that right here. So if we have half of the molecule dissociated, that means 50% of the molecule has gone to conjugate base, and 50% of the molecule has remained as intact acid. We would have this proportion equal to 1. Let's say this value up here is, there's 10 molecules of conjugate base. Well, if that's 50%, then the other 50% is 10 molecules of intact acid. 10 over 10 would be 1 here. The log of 1 is 0. And so this all cancels out. So when the amount of conjugate base is equal to the amount of intact acid, when we have 50% dissociation, all of this equals 0, and therefore the pKa equals the pH of that solution. pH is also critically important to us because much of the biochemistry that we'll be talking about in this course and the chemical reactions we'll be discussing occur in a very narrow window of pH, most of it occurring at the neutral window. Any deviation away from that narrow window, either becoming too acidic or too basic, can cause the enzymes to break down and the reactions to stop entirely. Chymotrypsin is a molecule that functions in cells. It functions best at near neutral pHs. As soon as we get to 6 or 10, we deviate by 2 pH units on either side of chymotrypsin's optimal pH, and we see that the activity of that enzyme drops off precipitously. Enzymes do not like acidic or basic solutions. Pepsin, on the other hand, has an optimal pH of 2. But again, if you deviate by 2 pH units towards the right and make it too basic, we drop off to about 30% activity. Another 2 pH units and pepsin is completely inactive. Where do you think pepsin functions? Where do you think pepsin is active? If you said the stomach or the gut, you're absolutely right. That is the primary acidic environment in our bodies. Pepsin is a digestive enzyme, and it has evolved to function best at an acidic pH because that's the environment of the stomach. It's worth noting, too, that we can also have polyprotic acids. Just as the name suggests, these are acids that have more than one proton to give. Each proton has its own Ka, its own pKa, its own dissociation constant. Some of those protons are very easy to lose, making it a strong acid. Other protons of the same molecule are difficult to lose, making those specific protons weak acids or strong bases. We see here a table of the different pKa's or Ka's in this case for the different protons in sulfuric acid. Sulfuric acid gives one proton up severely readily. The second proton is a little bit harder to give up, but still pretty high. We can see the same for phosphoric acid. That first proton comes off at a pretty reasonable window, about a pH of 3. That's a strong acid. The next one comes off at a pH of 8. Okay, near neutral, pretty strong as well. You want to get that last proton off of phosphoric acid? Well, you need a pH of around 13, and that's a very basic pH. Phosphoric acid does not want to lose that third proton. It holds on to it very tightly. So the reason why each of these protons has its own pKa is because each of these protons is given up with a different affinity. Some of them are given up very easily, and others are held onto very tightly, and pKa is nothing more than a measure of how easily a molecule will give up its proton or how tightly it holds on to it. So that brings us finally to the idea of amino acids acting as acids and bases. Histidine is one of the most nuanced and important amino acids we'll discuss, and we'll come back to histidine many, many times in this course in many different contexts. Histidine is important for cells because it allows a very unique feature. Its side chain allows a molecule to have essentially charge on demand. If you want a molecule to be charged, you can have histidine in there, and you can have a positive charge when you want it. but you can also get rid of that positive charge when you want to as well. And the reason for that is because of the pKa of that proton. The pKa of the proton that histidine can donate is about 6, close to neutral. What that means is that at the neutral physiological pH of 7, some of those histidines will have their proton and some will not. And so cells can control when histidine has its proton and is positively charged, and when it loses its proton and reverts to being neutral, by controlling the pH around that histidine. We're going to see how this is hugely important for enzymes as we delve into how enzymes do their jobs and what enzymes are. Many, many times it's important for an enzyme to be charged. Sometimes it's important for an enzyme to not be charged. And it's a pretty rare feature to have this ability to contain charge when you want it and get rid of it when you don't. And histidine allows that to be possible. So at very, very low pHs, where there's a high concentration of free protons, histidine will be completely protonated, and it will have a charge of +2. Every single part of histidine that can accept a proton will accept a proton. It is acted as a base, and it is fully protonated, +2 charge. If you shift that pH towards more basic levels, the pH increases, histidine will begin losing protons. The first proton it loses is from its carboxy group. We see that proton is lost here. That proton was present, and now it's lost. Since we have lost a positive group, we revert from a +2 charge to a +1 charge. We lost one positive. As we continue to shift to still more alkali basic environments, we see that the second proton we lose is off of the histidine side chain itself. This is the neutral form of histidine that we mentioned before. If you go all out and put histidine in a very, very alkali environment of a pH of around 10, it has lost all of its protons, including the proton here on its amino group. And so now that histidine has a negative charge overall. It has lost a total of 3 protons. So by shifting the pH of the environment that histidine is in, we can toggle between these protonated and deprotonated states and shift between having charge and not having charge, which is pretty unique. Because the amino and carboxy groups are typically involved in the peptide bonds, we'll talk about that a little bit later in the course. All amino acids can donate or accept protons from their amino or carboxy groups. What's unique about histidine is that it can do the same from its side chain group, that this proton can be gained or lost on demand as we toggle just in front of or just behind neutral pH. So, as a review of this material, think about this question. If we have an acid, and that acid has the pKa property of 5, and the pH of that solution that the acid is in is 3, what do you think the state of the acid is going to be? Will it have donated most of its protons or not donated most of its protons? Why don't you go ahead and pause the lecture and think about that. Say your answer out loud so that you can have some sense of whether or not you followed along well enough. I'll wait just 2 seconds here and then answer the question myself. If the acid has a pKa of 5, that means the acid will have protons ripped from it at any pH higher than 5. It will have those protons stolen. The acid will keep its protons and remain protonated at pHs lower than 5 in acidic environments where there's more and more free proton around. So if we have an acid with a pKa of 5 and it's in an even more acidic solution with a pH of 3, that acid will not have donated most of its protons. In fact, that acid will be heavily protonated. If an acid has a pKa of 8 and the pH of the solution that that acid is in is 10, do you think that that acid will have donated most of its protons? Yes or no? Same thing. Why don't you pause it, think this through, say your answer out loud. I'll wait 2 seconds and answer it myself. So we use the same logic, but we'll come to the opposite answer. If an acid has a pKa of 8, that means that if that acid is placed in a solution with a pH of 8, it will have lost half of its protons. Here, that acid is in a solution of a pH even higher than 8. That means there's more base around to rip even more protons from that acid, more molecules hungry for those protons. So if an acid with a pKa of 8 is in a solution with a pH of 10, that acid will have donated well more than 50% of its protons. Acids give up protons, bases accept them, and whether or not those acids have donated their protons depends on where the pH of that solution is relative to the pKa of that acid. Strong acids fully dissociate in water, and the same is of strong bases. pKa is a measure of the strength of an acid. The lower the pKa value, the stronger the acid is, the less base you need around to pull that proton off. So we'll leave this lecture there for now, and we'll just come back to wrap up these ideas in the big picture and summarize all of the concepts that we talked about in these lectures in the last part D unit of this lecture series.